We introduce a new topic, the topic of elasticity right now, and we're going to focus on a very important idea, at least for me it's important, called the Airy stress function. Before we get into the Airy stress function, though, let's take note that there are really two main categories of elasticity problems. There's plane stress and there's plane strain. Most of the problems that you've dealt with up to this point in your career have been plane stress. So that means the thickness of the element, whether it's the width of the beam or the thickness of this hockey puck thing, are relatively small compared to the other dimensions of the structure. But more importantly, the load here does not vary through the thickness, so there's no gradation of load here. And then finally, there's no out-of-plane component, so nothing has a z component. So that means that sigma z is 0. That's called plane stress. But what about epsilon z? Is epsilon z 0? And the answer is no. That would be a horrible mistake to say epsilon z is 0. Epsilon z is definitely not 0 because of the Poisson effect. Plane strain is sort of the reciprocal of that. It's the thickness is large, or that the deformations are constant through that large thickness. Here, sigma z is definitely not 0. So a way to imagine this is that there's two plates that are immovable, and the fact that they're immovable means that epsilon z is equal to 0, but sigma z is certainly not 0. It's doing a lot of work to keep that thing from expanding. So we can express strain as a function of stress in the generalized Hooke's law, or we could express stress as a function of strain. Both of those are very easy to find in the book, and you could actually derive it algebraically. So since we know that sigma z is important, it is 0 here in the generalized Hooke's law, and that would be, what? Would that be plane stress or plane strain? That would be plane stress. Then we take our generalized Hooke's law, and the normal strains now are expressed as 1 over e times sigma x minus nu sigma y. Some of you are still struggling with this Greek letter nu. That's a nu, that's not a v. And epsilon y has the Poisson effect on sigma x. So those two are normal strains. The shear strain, of course, is related to the shear stress through the shear modulus. This is Hooke's law for shear. And G is not independent of E and Poisson's ratio. So these things are super linked together for isotropic materials. So we can express strain as a function of stress and E and Poisson ratio so that we don't introduce that G. Then looking at the Chapter 2 compatibility equations, remember that compatibility has to do with deformations. And it really starts with the shear strain equation. The shear strain is partial V partial X plus partial U partial Y. We've seen that many, many times. The next step is that we're going to differentiate this with respect to X, and then we're going to differentiate it with respect to Y. And the order does not matter, so I'm just going to do one and do the other. So once with respect to X, and once with respect to Y. And what do we get? We get partial squared epsilon x partial y squared plus partial squared epsilon y partial x squared. So what the heck? How does that happen? So I have a little explanation in here in the board notes here. So let's just take a look at this. Remember I said we're going to do it once with respect to x and once with respect to y, and the order doesn't matter. So if we do it once with respect to y, we have partial v partial x, and we're going to differentiate that with respect to y. And then we have partial u partial y, and we're going to differentiate that with respect to y. Now we're going to take that with respect to x here. So we have partial x, partial y, partial v partial x, and then partial x in front of this, partial y, partial u partial y. And partial v partial x, partial u partial y. That doesn't make a lot of sense, but how about partial v partial y? Then you have the two x's out there. and partial V partial Y is epsilon Y. That's the red one. Partial U, pull this one out first, and then you have two Y's. Ta-da! So that's pretty sweet. And remember what those mean. They're the change in angles here.